All right, students, let's do a little video solution here so you can kind of look over exam one, self-grade it, find your errors, and also get a rough idea of what you would get for your score. Start with number one in the multiple choice here. It says a roller coaster has a mass of 500 kilograms, fully loaded with passengers. Okay. So at the bottom of a circular dip of radius 40 meters as shown, the car has a speed of 16. What is the magnitude of the force? So this is a Newton's second law. Sum of all the forces equal to ma. If we do a free body diagram, we'll say that, okay, gravity is pulling it down, that's weight, track is pushing it up, that's the normal force. And that's it, as you've heard me say many times, it's gravity and everything touching it. So if we go ahead and apply this, we would have normal force and then weight. And in this case, since we are turning on a circle, and that was the whole point of this particular chapter, I guess this is chapter 6, that there would be acceleration, and when it goes in a circle, it's v squared over r towards the center of the circle. In this case, the center of the circle is upward, so it's a positive. And then that kind of makes sense because then this is saying that the answer is the weight plus a little bit more. And so if it was just a level track, the normal force has to be the weight. That weight can go in a straight line. So there needs enough force just to make it go in a straight line. Otherwise, gravity drops it down. But then to curve upward, to be accelerating upward, we need an additional mv squared over r for this upward force. So this would be 500 times 9.8. And then another 516 squared over 40. So grabbing our calculator here, 500 times 9.8 plus 500 times 16 squared divided by 40 is 8,100. And so answer B, for the first one there. All right. The second one is also out of chapter 6 here, Newton Universal Law of Gravity. We have two stars. We have one that has a mass, so two stars have a mass of m, and the other one is over here with 6 times that mass, 6m, and they're a distance of 100. I'm not sure the wording's so great. They talk about stars, and they'll put them only 100 meters apart. Maybe it should be two objects. Not necessarily stars. But in either case, determine the distance measured from M, okay, to a point where the net gravitational force on a third object, so third object, I'll make a little colored in and give it a little m, would need to be 0. Now, for this one to come out to be 0, you have to have a force that are equal and opposite. So the little m is going to be attracted to the big M, and it's also going to be attracted to the 6m, 6 big M. And then they have to be equal in magnitude and opposite direction. So the opposite direction means that little m has to be somewhere on a line connecting the two. It can't be off to the left or off to the right or even above or below. Those would not get you opposite in direction. So we know it's got to be somewhere along this connecting line. All right, then also to be same magnitude means we're going to have to be a little bit closer to the M than the 6M, because the 6M is going to give us a force greater due to the mass, but we can make up for that by being a shorter distance. So if we call that distance x, and then this becomes 100 minus x, we go to calculate the force between these two. We've got G, capital M, little m over x squared. And between these two now becomes G, 6 capital M, little m, and its distance would be 100 minus x squared. And given that there is the universal gravitational constant on each side, I can cancel those. Also could cancel the big M and the little m. And so we're only left with a 6 over here and, well, nothing. Well, there'd be number 1 over here. So if we cross multiply, this becomes 100 minus x squared, and this becomes 6x squared. taking the square root as we try to solve this gives me root 6x. Moving the negative x to the other side means I got a root 6 plus 1. I'm going to get a number for that. Root 6 plus 1, 3.45. So 3.45x, or x is 100 divided by that last answer. And so it looks like about 29. So it looks like answer D would be the correct answer for number 2. All right, and on to the other chapters. Here's a interesting one, kind of on the hard side, actually. And actually, these weren't so easy either. Yeah, we got some harder material here. But not too bad yet. I think they're going to get hard. Okay, so then this one, we have a 2 kilogram block, slides down frictionless. Oh, good. Usually a little easier with frictionless incline from point A to B. So it looks like it's moving down to B. But there is a force P of 3 newtons acting on the block from A to B as shown. So there is, something holding up. Maybe this is something falling downhill and somebody's going, no, stop. But it's still going downhill. So the push is, well, in mathematics, we'd say it's doing a negative work. It's actually slowing it down, and we can see that from the work energy theorem. And that's what's going to make this probably the harder part of here. Points A and B are 2 meters apart. If the kinetic energy of the block at point A is 10, so it's already moving down here, what is the kinetic energy at B? Okay. So it's going to look, I guess, something like this. This is the idea that the work energy theorem says the work you do is equal to the change in kinetic energy. So maybe I'll deal with that first. Final minus initial. So we are after this final. What is the final kinetic energy? And the initial is 10 joules. Okay, now the other side of the equation is the part that we need to think about here. Maybe I'll just kind of do a free body diagram over here. And so our forces would be the force of gravity, pulling it down like that, and everything touching it. So we've got the normal force, no friction, and then we got this force, P. And it moves along this direction. And the key here is that if you remember, work is this force dot distance. Put a little R here. But basically, it is the force, what we call parallel to the distance it moves. So, in other words, the normal force is irrelevant here. There is no component of the normal force in the direction it moves. And so the force from the incline doesn't make it go faster or slower. And then you can see the force of gravity. Maybe I'll change to a red color and do its components. There'd be a component down the hill and into the hill. And we've done that many times in the previous chapters, and so we saw a bunch of this on the first exam. But what I'm going to take advantage of here on the second exam here is I only want the amount of force that's down the hill, which we've learned more than once. It's mg sine theta. So in this case, 30 degrees. And so of the force of gravity, I only need this component of it. And it's in the direction it moves, so it's positive work. Now, fortunately, the P here is exactly opposite. So it would be negative. It would be, if you wrote this out as FR cosine, you would write it as then 180 degrees, since the distance it moves and the amount of force then is negative. So when we say here how much work is done, we have this. We have an mg sine theta for the force, and the distance from A to B. Let me just call it R for a moment. That's a positive work. Whereas then we're going to add a negative work, which would be the force of P times the distance it moved. And that has to equal to the final minus 10. So that is, I guess, Mara, I might say, this gets to be a hard problem because there's two steps to the work, and there's, I guess I'll call it 2 steps for the kinetic energy. It's final minus initial. We have an initial, so don't overlook that. All right, so let me put in the numbers. So this right here is a 2 times a 9.8. Sine of 30 is 1/2. And R is 2 meters, right? From A to B is 2 meters, yeah. And so this is then a 3 and a 2, and then final minus 10. And they were kind of nice here because those cancel, and this is almost 20. And 7.8. Yeah. Is that right? I guess so. Just looking if I should round it. And I think so. Maybe I better not. That's what I get. 19.6. All right, minus 6 equals final minus 10. Okay, so 19 minus 6 is 13.6. Add 10 to the other side, and we are looking, 23.6. Okay, good. And if I would have rounded, I would have gotten to 24 even. And so the two significant figures, it is 24. All right. Sorry, mentally I got sidetracked on the whether I should round this or not, and I'm glad I didn't. Anyway, so it rounds to 24 with two significant figures. So there's a C. Moving on to number 4. Here is a 2.5 kilogram ball fired vertically, hits the floor with a speed of 2.5 meters per second, rebounds with a speed of 1.5. What is the magnitude of the impulse? Okay. So impulse, I guess we have 2 options to go. Unfortunately, neither one is too difficult. One, which I don't think is the one we want, force. If we know force and time, we can have force times delta t is the impulse, change in momentum. But also just change in momentum would be, final momentum minus initial. And I think that's the way to go, because we have the final speed and we have the initial speed, and momentum is just mv. Okay, and so these are given straight up. So good. This is more of a definition type of question about what is momentum, because we have 2.4 times a final speed, and so the final speed is 1.5 up. And the initial speed, so here's the mass 2.4, is 2.5, but it's on its way down. So if there's anything kind of hard about this one, is remembering that momentum is a vector and it has direction. And so usually we call up positive. So I'm going to call the 1.5 up as a positive. But that makes the 2.5 then a negative. And then the two negatives cancel, and we're essentially adding these two together. So mathematically, we would be 2.4 times 1.5, which is a 3.6, and then a 2.4 times a 2.5, which is a 6. And so that's 9.6. And so 9.6 would be the first one there. Answer A for number 4. Okay. On to number 5. An 8 kilogram object moving at 4 meters per second in the positive x direction has a one-dimensional collision with a 2 kilogram object moving at 3 meters per second in the opposite direction. Okay, so we've got this head-on collision coming here. The final velocity of the 8 is a 2 in the positive direction. Okay. What is the total kinetic energy? All right, so this is going to take 2 steps. So maybe this is kind of a hard one. It's pretty straightforward, but it is kind of hard because of the 2 steps. So I'll start with the conservation of momentum because we have an 8 kilogram object moving at 4, next direction. And we have a 2 kilogram object moving at -3. So there's what we just said in the last problem. Be careful with your directions and your momentum. And 8 times 4 is 32 minus 6. So that makes 26. So we have 26 units of momentum here. And the principle of conservation of momentum says we have to keep that. All right, so after the collision, and they don't stick together apparently. They don't say that. Those are kind of the easier ones. They just say the final velocity of the 8 is still 2 in the positive direction. So the 2 has some unknown speed. So 16 plus 2v, 26. Subtract that. 10 is 2v, or v is 5. So there's kind of that first step. Is what is the speed? And it would be easier problem with all that they asked. But now they go on to say, what is the total kinetic energy? All right, so the first one, this one here, would have 1/2 times 8 times 2 squared. That's our 1/2 mv squared for the kinetic energy. And the other one's going to have a 1/2. Its mass is 2, and its speed is 5 squared. All right, so let's see. Half of 8 is 4, and then 2 squared is 4. 4 times 4 is 16 joules from that one. Those cancel, and this is 25 from this one. 11, so that's 41 joules, and it looks like C would be the answer when we get to that second step. And I keep looking at like the lens is a little blurry, but I think it just might be my angle, but I'm going to kind of wipe it there a little bit. Okay, going on to number 6 here. Number 6 says we have a 12-meter long crane supported at its lower end by a pin, so here, so it can kind of pivot, is elevated by a horizontal cable. So there's some cable with some tension here. A 250 kilogram load is suspended from the other end of the crane. The weight of the crane is negligible. What is the tension in this cable? All right, so you can see then that we've gone on to rotational motion, some of the harder mechanics. And so this can pivot, so it's being pulled by this tension in a counterclockwise direction. And this one here is pulling it in a clockwise direction. And when it comes to rotations, then those torques have to match. Not the forces, but the torques. And so I'll call this one up here the torque that is, let's call it counterclockwise, and then this one clockwise. And so if you remember our discussion on torque, it's the force and the perpendicular distance. So if this is 12 and that angle's 60, we can get the perpendicular distance by doing cosine of 60. So the force is tension, perpendicular distance is 12 times cosine of 60. And then the torque, the other direction, would be the weight of this block. So I'll call it 250 times 9.8. That's the force. And then the perpendicular distance would be this right here, which would be the sine of 60. So it would be 12 sine of 60. And 12 is going to cancel off. And so the tension would be the 250 times 9.8, that's the weight, and then multiply by this factor, which is sine 60 over cosine 60, which, by the way, is tangent 60. All right, so grabbing my calculator, 250 times 9.8 times a tangent of 60 is about 4,240. 4,240. 1, 2, 3, 4. All right. So I guess that'd be D. Nice. All right. Oh, more rotations. And so the last one, we had torques in opposite directions. One clockwise and one counterclockwise. These are the same direction, both counterclockwise, so I guess a positive torque is our tradition. But they go together, and so I think that's the point of the problem, what is this net torque? And so net torque, like net force, is you just combine them together. If you have two, you combine them together. But again, torque is this whole idea that they are related to distance. So the distance from O to A is 10 centimeters, which I'm going to write as 1/10 of a meter. And the force is 20 newtons. The other one is a distance of 0.2 meters, 20 centimeters right there, and has a force of 40 newtons. So this would be 2 Newton meters, and this would be 8 Newton meters. 2 times 40 is 80, yeah. And so adding together, it's 10. And you can see that this force over here, that's twice as much, and also twice the distance, makes it 4 times the amount of torque as that one. So that's why that's an 8, and that's only a 2. And then together, of course, it makes 10. So that would be B there for number 7. All right. Moving on to, I guess, number 8 here. Again, more rotations. We got something pivoting up here. It is a 1.5 meter long rod, and it's a mass of 2.5 kilograms, swings freely from one end. The rod hits a stationary 1 kilogram round and small rock at the bottom end as shown. The rod is swinging with an angular velocity of 6.2 radians per second before impacting the rock. The rock sticks to the rod. What is the angular speed? So this is like the collisions we did earlier. But earlier was, here we go, number 5, a conservation of linear momentum. This is a conservation of angular momentum. So this would say the angular momentum initial is equal to angular momentum final. And so when we do angular momentum, instead of having mass, we have moment of inertia, and instead of having linear speed, we have angular speed. And so in this case, before the collision, we don't have to worry about this rock. It has no speed, but the moment of inertia, if you go back to the textbook there, you'll see that the rod pivoting around its edge is 1/3 times its mass times its length squared. And then it's, of course, its initial speed. So in this case, that angular momentum is 1/3, so 1 divided by 3, times a mass of 2.5, times a length of 1.5 squared. So we have a 1.875 for the moment of inertia of the rod, and an initial speed of 6.2. Now, on the other side of the equation, the inertia would be the two objects. And so we would have the rod again, which we just figured that one out. And then we have this little, I'll call it a point mass because it said it was small, and that's just m times the distance squared. So 1.875, and so its mass is a 1, and its distance would be 1.5 meters from its pivot point. And 1.5 must be 2.25 because it's 15 squared with a decimal place. All right. And so if I add that to the inertia of the rod, this side is 4.125. Okay, so taking the inertia of the rod times 6.2 and then dividing it by the other side, I should get a speed of about 2.82, or just 2.8 for two significant figures. And so that would be B. Yeah. For number 9. You know what? I just realized. Did I skip that one? I did. I'm sorry. I went to look at something and skipped number 8. All right, because I was like, I thought I was doing number 8. All right, so I did number 9. I apologize for doing it out of order. Let's go here to number 8. Looks like a little calculus here. It says a wheel is rotating around a fixed axis with an angular position given by this equation. What is the angular acceleration? So maybe you remember that acceleration is the rate of change of angular speed, and angular speed is the rate of change of angular position, meaning that angular acceleration, when you put all this together, is the derivative of the derivative of the angle, which we write as the second derivative of the angle. All right, so let's take the first derivative. So d theta dt. The derivative of a constant number is 0, minus, and to do a derivative, you bring down the 3 multiplied by the 2, that's a 6.0, and you reduce the exponent by 1. Okay. Doing the derivative a second time, and we'll ignore the 0 now, negative. Bring down the 2 with the 6, that makes a 12t. Okay, so that would be the equation for alpha. And we're to evaluate the angular acceleration when time is 2. So this would be negative 12 times a 2, which is negative a 24. And so B should be the answer to number 8. And then also B for number 9 that we did out of order. Okay, and then the last of our multiple choices here, number 10, it says, some species of whales can dive to a depth of 1 kilometer. What is the total pressure? So the pressure would be the pressure of the atmosphere plus this additional pressure due to the fluid, which is the rho GH. So the atmosphere is 1 atmosphere. But the pressure, at least done in SI units, would get pascals, which then we can convert to atmosphere because it looks like our answers are all in atmosphere. So rho, let's see, the density of the seawater is 1,020. G is 9.8. And again, just being a little careful with the units, 1 kilometer is 1,000 meters. So the pressure, at least in pascals, would be 1,020 times 9.8 times 1,000. And then this says that 1 atmosphere, and I guess to 2 significant figures that's true. I think it's 1.013 times 10 to the 5. I'm wondering if I should use more, 3 significant figures. Well, I better do what is given. I don't think it's going to change it by enough. It's only 1% difference. But so let me divide that by 100,000. So 1,000. And so, yeah, the 3 significant figures, this is 100 atmospheres. And so together, we get 101 atmospheres. So answer C. And it would be tempting to drop that, but it'd get you 100. But fortunately, there's no answer that there's 100 there. So, all right. Maybe I'll hit pause there and do the free response on a second video. All right. Take care.